So this will be my final lecture regarding the chapter 7, superposition, and I will be speaking the very rudimentary introductory basics about coherence. So coherence is a strange concept when we are dealing with waves, and really in practice it's always present. So it's like quantum mechanics in physics, that in the end it's always present there when we are describing waves. But most of the time when we are dealing with introductory things, we can even almost always forget entirely the fact of coherence. And this is really hard concept to understand, and probably the difficulties arise from the fact that you are not yet familiar enough with the math that is used to understand coherence. So because then we don't have mathematical tools to understand things, then it becomes quite hard to try to structure things and the physics in your own mind, because you lack the mathematical framework. But on the bright side, this is an introductory course, so we don't need to be able to quantitatively understand coherence and coherence properties of light sources. So we can just be fine and happy by just introducing the main notions, and we can leave the more specific quantitative rigorous treatment of coherence to the upcoming courses and follow-up things. So I hope you get the main notions, but I just wanted to warn you in the beginning of this lecture that this is actually a very complicated, nuanced topic, and this is in a way always present, maybe not explicitly mentioned when we are treating things, but always under the hood. So implicitly you should be thinking also about the coherence properties when we are thinking of treatment of light and superposition of light of several different frequency components or several different plane waves. So this is what I wanted to say, I think. So let's look at the concept of coherence. We have been summing and considering propagation of time harmonic plane waves. And of course, a time harmonic plane wave is a purely mathematical concept. So it's basically just a mathematical description of a propagating wave. And this is not something that is physically realistic. And with that, I mean is that we can never realize anything in a lab or in any kind of physical setting that would be a time harmonic plane wave. So that's entirely mathematically or physically impossible. And the trouble here is that we would be dealing with a wave that oscillates harmonically. And since it oscillates harmonically with just a single frequency, please note the conjugate pairs between time and frequency. If you have something that is oscillating only at a single frequency, it means that it's oscillating, keeping its phase from minus infinity to infinity. So essentially, this is the downside of treating waves as time harmonic plane wave quantities. And here, what this means physically, that the wave oscillates really harmonically with respect to time from minus infinity to infinity, that whenever we are looking at the phase of my field, and let's now look at the phase at an instance of time of t1, and then look at a second instance of time of t2, these two phases are perfectly correlated between each other. And this tells me that in fact, or when this is the case, I could say that the wave is fully coherent. And wave is fully coherent between these two occasions of time. So between these two time intervals, between them, the wave would be fully coherent, meaning that there's a perfect correlation between the phases. And essentially, I could describe things, my field, essentially just using a single time harmonic wave quantity. And here, since I'm dealing with a time harmonic wave, then in principle, this separation, this distance between the two different intervals of time, t1 or occasions of time, t1 and t2, becomes arbitrarily large. So I could have a very small number as a t1 and a very large number as a t2. So in principle, this could be at the kind of like, I don't know, 0 time, and this could be the largest time interval I can imagine, 14 billion years or so. And of course, this becomes unphysical as a concept. We really cannot realize that kind of oscillations because that's just physically not possible. Graphically, how things would look like is that the things, or at least this is what I'm thinking myself when I'm thinking of coherence. So I'm just drawing a single time harmonic wave, and it's oscillating like this, and between these two different time intervals, the field looks exactly beautiful time harmonic oscillation. So just a sinusoidal oscillation with respect to time. And now that I now know, or if I happen to know what is the phase of my field here, I can instantly calculate what is the phase before every occasion of time. So I can exactly reproduce, and I know entirely how the field looks like until time occasion of t1. And this is now when I'm really having a perfectly coherent light distribution. So let's say perfectly correlated the phase distributions between the different occasions of time. Now, how we get a little bit more physical treatment of a light distribution, we can assume that we have a light distribution that consists of several wave packets, and this is usually the starting point to understand coherence. And now all of these different wave packets, inside them we have perfect coherence, but when we are looking at the light distribution between different wave packets, we are no longer having coherence between the different wave packets. And then essentially the coherence is related to the kind of correlation between the phase distributions, so that if you would want to know what is the phase of my light distribution at a given instance of time, as long as I'm inside a single wave packet, if I would happen to know the phase at a given instance of time, I would know right away what is the phase instance on these other occasions of time inside that wave packet. But if I want to go into another wave packet and understand how the field looks like in there, I'm no longer be able to describe the relation at all anymore, because I don't have coherence anymore. So essentially, graphically, this is a common notion how things are being drawn. So I have my wave packet here, and the wave packet, the time duration can be described using a tau c, so a coherence time associated with my light source giving rise to these light packets. And if I know the field here, if I know the phase of my field here, I know what the phase of the field would be inside this wave packet, but I would not be able to tell me what I would have my phase inside a different wave packet. So essentially here, please note there's a phase discontinuity there, and that breaks the correlation between the phases. So each wave packet is still oscillating at the same phase, so that the frequency of my sine wave is the same, but here it's just kind of breaking down into a single different portions, and the phase jumps when we are looking at a different wave packet. And this description, of course, it's simplistic and it's not very rigorous in terms of mathematics, but at least qualitatively it gives us the right picture, and it's very easily drawn in terms of these kind of graphical description. So that's why we usually use this kind of description when we are introducing coherence to students. So we're looking at the phases of the wave, and we are looking at the phase at different time instances again, so at t1 and t2, and as long as they are perfectly correlated, then we say that the interval or their difference is smaller than a so-called coherence time. So this is how we, in a way, define a new quantity, this coherence time, described as this guy here, and that is defined by just looking at the kind of correlation between the phases of my field, and as long as there's a correlation between the phases, then I know that the coherence time is larger than their separation. So essentially, this is how I would be able to estimate the coherence time. Equivalent way of defining things, what is the coherence? I could also define a coherence distance LC, and that is essentially the coherence time tau c multiplied with the speed of light c. And now the same way I could try to calculate their difference. So two different locations, L1 minus L2. And as long as this is smaller than the coherence distance LC, which is equal to the tau c times c, then I would have a phase coherence between the two different locations. So this is how things would look like. And there's these two ways of looking at it. Either we look at the kind of coherence time, so how long intervals the phase coherence retains in our wave. Another way of looking at it would be that how long light distribution can be propagating, that I would start losing my phase coherence. So depending on what kind of interference experiments you would do, it might be smarter to use the different kind of approach and picture to try to understand what happens for coherence. And then the final slide. This is the third time I'm apologetic. This is a simplified situation. So in real life, we should really take use of stochastic electrodynamics. So we should really take into account the statistical nature of light distributions, and that would be the proper way. So in reality, what I'm trying to say here is that the coherence of a wave is not really a binary property, that do we have coherence or not, but rather it's a kind of a continuous quantity that how we define a light distribution. And when, for example, we are looking at different time instances, the coherence properties do not suddenly vanish, but rather they smoothly decrease when we are increasing the time separation. So we are increasing the difference between T1 and T2. So that this is, for example, a one aspect of more realistic coherence properties of light sources. So it's not a binary property, but rather it's a kind of a more continuous variable. And of course, a more formal treatment, like we would really need a totally different way of describing light distributions. So we should really looking at the kind of sums of many waves where we should really have a random variables placed so that we would have some kind of stochastic distributions. And then we should really look into the statistics of that kind of distributions to understand of their coherence properties. But that kind of level of mathematics actually is quite complicated. So we do not deal that at all in our introductory course. But here I will stop by just showing you that in a nutshell, what you need to understand of coherence properties in the framework of this course is that in the red curve, I'm highlighting a case where I have a perfectly correlated field. And when I have a perfectly correlated field, that essentially just means that it's a time harmonic wave. And then that means that the correlation exists in time variables in different occasions of time for the phases, from infinitely small time t to infinitely long time of t. So in a way, coherence means that how well can we describe the plane, our field, as a time harmonic wave. And if we can really describe our fields very accurately using a single time harmonic wave, then we can say that our light distribution is coherent. But in more realistic scenarios, I cannot anymore describe my light distribution as a single plane wave, time harmonic wave, but rather, for example, I should describe it using a kind of many different pulses, and then I would have some kind of random phases associated with different pulses. And then I would be introducing some kind of quantity known as a coherence time or coherence length distance that would tell me a little bit about the kind of how long the correlation persists in the fields. So that how long I could still describe my field distribution as a single simple time harmonic wave. So this is basically what I wanted to say in this lecture. But please ask us more, as teachers and teaching assistants. Coherence is actually a very tricky thing, and you probably need quite a bit of dialogue to get a better understanding of this concept in your journey to become a master level 86 Optics Pro person. So thanks for listening these lectures I had on chapter 7, superposition, and this was basically a prelude for the upcoming chapters. So chapter 8, interference, and chapter 9 regarding diffraction. So basically now we're applying this math I have just introduced to you, and then we want to understand what kind of effects and phenomena actually take place when we are summing fields together. So thanks for listening. Congratulate yourself for going through chapter 7 with me, and please enjoy the rest of the week and join me shortly when I'm starting my lectures again on chapter 8. So thanks. Have a good day, good morning, good evening, good night, and good week. Thanks and bye-bye.